So constants independent of the input do not matter. So what am I saying? And keep in mind there's several different ways you could reformulate this property, and it will still probably be true. It works like this. So what I'm saying is if k is a positive real number, and you know that f is big O of g, then it also has to be the case when you multiply k by f, sorry, I'm getting very excited about my f. That's a little bit of a wide side there. K times f has to also be big O of g. So what does that mean? So if you're talking about something that has a multiplicative constant like this, and you know that this is just some constant, it doesn't relate to n at all. But if you just find out that f is big O of g, then it's no different than if I just, like, it follows that it also has to be the case when there's a constant in place. There's several other ways you could reformulate the same statement. This is just saying that the constants don't matter. That's what it's essentially saying here, is that you get this if you know that's a constant and you know f is big O of g. You could, like I said, you could also rewrite this in several other ways too. But this is the way I'll present it to you. So here's a proof. Now, notice that this is actually a conditional statement about two arbitrary complexity functions and also a constant. So you have to keep in mind that often if you're not sure about how to start with a proof like this, you can start off by writing out, like, consider any k, f, and g with the appropriate domains in place for them. But what I'm going to do is I'm going to take advantage of the fact that I have this and this being true to follow this statement. So remember, this is a conditional statement. You can think of it like a logical test. So you might know this, like, say in programming, you might know of an if statement. So what you might say to yourself is, Dan, if this and this are true, then it must be that this follows, right? So all I'm going to do is I'm just going to take these two and say, hey, look, if this and this, then it has to be that this is the case. That's what we're trying to prove here, right? So I could take these in my proof as givens, and I can use them to deduce the consequent of our conditional statement. So that's where I'm going to start here. As f is big O of g by the definition of big O, by the definition of big O, so by the definition of big O, we have the following, right? It means we have those two constants, right? We can use them. So for those that are inclined for fancy terminology, if I give you a statement like this, what it really is saying is that I get those two constants for free, right? That's what it's saying. So we call this an existential instantiation when I want to use those constants, because this is actually a statement that talks about the existence of certain constants such that the inequality is true for all n is greater or equal to n0. So if I know this is true, then it means that I can instantiate, almost like I'm declaring variables, those and give them names by the definition of big O. So I'm going to give them names. There exists C prime. I'm not going to call it C and N0. I'll call them C prime and N prime. Like I said, I can give them names. So C prime and N prime, which is a positive integer, so that for all, remember, all I'm doing is writing out the big O definition now just for f and g. For all n greater or equal to n0, it has to be that f of n is less than or equal to c prime times g of n for all n greater or equal to n prime, right? So now we have this. So we can use this information. Now, because I've laid this out, now keep in mind I didn't have to state this first. I could have stated it after this. What I'm now going to talk about is what I'm going to do to ultimately prove this claim now. So we're just as usual, I'm just going to say what I'm going to do, the game plan. We find constants, C, which is a positive real number, and n0. That n0 is looking a little too much like a no. I'm going to need to fix that. n0, which is a positive integer, so that for all n greater or equal to n0, it has to be that f of n, well, in fact, it's not just f of n, right? It has to be that is k times f of n is less than or equal to c times g of n for all n greater or equal to n0. So that's what we need to do next. So I got some ideas here. Now remember, I have a constant called c prime. And that comes, so I know f is big O of g, so it means that I already have a couple of constants I can play around with, right? So the idea here is I'm going to pick those up, and I'm going to try to make it so that I can still scale the left-hand side. So notice it's k times f of n. I'm going to try to scale the right-hand side so it matches the fact that I'm making the left-hand side k times bigger. So this is how I'm going to go about figuring out the constants, okay? So remember that k is a constant. K is a constant. It's not, has nothing to do with f. This is going to be important for our reasoning here. So I'm going to say that as k is a positive real constant. It's important that it is a positive real constant, by the way. It can't be 0. You would have to do a little bit more massaging to make this work if that were not the case. We're going to pick C so that, remember, I'm going to try to make it look alike the left-hand side. So what I need to do is I'm going to make it so that I can get rid of the k on the left-hand side. So I'm going to try to put k somewhere in here. And then I'm going to try to multiply it by something that I know for a fact has to be true. So notice that if it's k times g of n, then I'll have k times f of n is less or equal to k times g of n. If I divide by k on both sides, then I end up with f of n is less or equal to g of n. But we know that actually isn't true for all n greater or equal to n prime, right? So you need to actually incorporate the constant that I have up here. So I'm going to pick that constant. So I'm going to take c as follows as k times c prime. Then we find n0 such that k times f of n is less than or equal to c times g of n, which is going to be equal to k times c prime times g of n. And now remember, as I said before, k is a positive real constant, so it means that we can divide by k. So I'll say constant k is a positive real number. You should write the full word number here. I'm just doing this for the sake of brevity here. So by dividing both sides, of the inequality, by k, we end up as follows. So I'm just going to write it over here, okay? So as I've sort of laid out here, is we know that we already have something that works. So why disrupt that? So we're just trying to pick the constant so that we could just massage that into our statement that we're trying to prove. Which shouldn't be very much a surprise or anything like that. At least we got a little bit of a feel for this. So So after we do this, remember we're going to have k times f of n is less than or equal to k times c prime times g, which this, if you divide by k on both sides, this is no different than me writing as follows. F of n is less than or equal to c prime times g of n. But what's this? Well, we already show that that is actually the case, right? We already know that this is true for certain values of n, which holds for all n greater or equal to n prime. So what should I pick for n0 then? Well, I should pick n prime, right? Choose n0 is equal to n prime. And then now we have two constants. Now you might ask, Dan, these are for arbitrary functions, and you didn't specifically give those like numeric values. So like, how do you know this actually works? Well, it's remember, the way the logic works in this statement is that if k is a positive real number and f is big O of g, you know that those two statements are true, right? So it's going to be that it follows from those two things. So you know you're going to have those two constants for this to work. So if you have those two conditions in place and they're both true, or at least they're going to be the case, then you should be able to plug them in appropriately here. So like I said, these are a little bit more general statements. So now I just conclude the proof by, of course, invoking the definition of big O, because we need to do that. Remember, you find the two constants, right? They're like, imagine you have like a barrel here and you're trying to find those two constants. So far I've done that. I've justified the two constants for you. I picked them, I have them in my hands. Now I need to present them to you and say, here's the conclusion. But I use the big O definition to do it, right? Therefore, by the definition of big O, we know k times f is big O of g. And we're done. So those constants independent of the input, they don't actually matter in terms of big O notation. In practice, they might. So I must stress that those constants, they're great to suppress when you're talking about general instances of your problems. And if you want to talk about this in a machine-independent manner. However, remember that still, when you're counting operations and all this stuff, or if you're timing things, those details do get lost sometimes in big O notation.